So while Carl has given you a good foundation on reinforcement learning, I'll talk about applications of machine learning to autonomous driving application domain. Since this topic is very new, there's no textbook, and so I have to discuss recent research papers. So I'll talk about imitation learning in this lecture. Reinforcement learning problem, you have an agent that interacts with the physical environment, and it's trying to maximize its cumulative reward. So there's a key. The key to reinforcement learning is the reward function, sometimes called the loss function, defined as the negative of reward function. So sometimes people say minimize loss, which is equivalent to maximizing reward. Model-based IR, you first estimate to identify the model of the physical world given current state as t, action at. What is the probability distribution of current reward rt, the next state st plus 1? So you're trying to figure out this relationship, how the physical world works. It's parameterized with the cellular parameters. For example, it could be a deep neural network. So once you have the model of the world, then you can do planning with value iteration or policy iteration. The job is much easier, but in most cases, you have to do model-free RL. So you estimate a value and optimize it without knowledge of the model P, including Q-learning, deep Q-learning, policy gradient, imitation learning. They're all model-free. Reward function. For this vehicle, the state is its pose. A pose is just its xy coordinate plus the heading, theta. So given the pose of the ego car, and environment map could be a circular track you saw before. The action are steering wheel, brake, acceleration. So you may define a possible reward function, weighted sum of the longitudinal velocity at this direction, and to maximize the longitudinal velocity and to minimize the cross-track error, distance to the lane center. So this expression is the combination of these two smaller objectives. So if you have this reward at every time step, then this is an example of dense reward as opposed to sparse reward, which is you only have the reward at the end of each episode. So your old friend Twiddle is actually a reinforcement learning algorithm, which is a policy gradient that learns PID parameters with sparse reward. So the cost function, if you remember, is the cumulative cross-track error computed at the end of each simulation episode. As the sum of squares of CTEs for n time steps. But this is a very crude reward function. First of all, it doesn't use the numerical value of CTE, only its relative size to the current best. If error less than best error, record a best error. Otherwise, do a bunch of adjustments to the parameter, PID parameters. So it doesn't matter if the error is a million or 10, as long as its relationship with the best error is the same, then the reaction of the twiddle is the same. And cost function only includes the cross-track error, not the heading angle. So the vehicle may be traveling, well, they are related, right? If the heading angle is non-zero, you are going left and right, so your CTE may be large. But it's good to have the heading angle explicitly in the reward function like this, so that you try to aim the car straight ahead. Try not to oscillate left and right. And also, if the track is very long and irregular, then we can make the reward denser to adjust PID parameters every k time steps instead of at the end of each episode. It's a common trick in reinforcement learning to make the reward denser by having intermediate rewards. So RL can be very effective, provided that a suitable reward function is available. But bad reward function leads to an undesirable behavior. Suppose you design a vacuum cleaner to maximize the reward function defined as the cumulative amount of dirt sucked in. The vacuum cleaner may learn to repeatedly spit out and suck in the same pile of dirt, thus maximizing its reward. So for autonomous driving in realistic environment, the goal is to reach destination with minimum travel time while avoiding accidents. But how to encode this complex behavior into a reward function? So in AWS, Amazon Web Services Deep Racer, they have a MOOC online, but it's a very simple MOOC. A great reward function can help you better optimize your IR model. In Deep Racer, the reward function is written in Python code and uses different input parameters to help encourage good behavior and disincentivize poor behavior. There is no single right answer for which parameters to include in your reward function, and your best reward function will likely require a lot of experimentation. So Amazon Web Services launched Deep Racer in 2018 for training AD algorithms with IR. So you can train IR in the simulator on AWS Cloud, but it costs money after some free time. So they also hold competitions both online and in real world. They sell this 1/10 scale race car that costs $349. So this is the figure from the documentation of Deep Racer, defining the parameters for writing your reward function. So all wheels on track, yes or no, X or Y position, distance from center, that's this distance, is left of center, is to the left or to the right, heading angle theta, progress, how far you are from your goal, steps, speed, larger the better, of course. Steering angle, the delta in the bicycle model, if you remember, and so on. So you have these parameters. Here's one possible reward function. So this is trying to penalize steering, which helps mitigate zigzag behaviors. So you calculate 3 markers that are at varying distances away from the center line. Marker 1 is 0.1 times the track width. Marker 2 is 0.25 times a tracker width. Marker 3 is 0.5 times track width. If the distance from center does not exceed marker 1, reward is 1. If it's between marker 1 and marker 2, reward is 0.5. If it's between marker 2 and marker 3, reward is 0.1. Otherwise, reward is almost 0. So, and steering threshold, if steering is higher than the threshold, the steering angle, then reward is decreased by multiplying with 0.8. So this tries to keep the car in the center, close to the center line, and try not to steer too hard. So that's a simple reward function. Let's look at a more realistic, complex reward function. So this is the track. You can design your own track. The action space are the maximum steering angle granularity. So you discretize the action space, not continuous. You have a discrete choice of 5 possible steering angles. And speed, maximum speed at speed granularity. Reward function. So you have the input parameters we saw in the figure, and if 5 less than 5 amp less than LT progress, this is not rendered very correctly. So our progress, if progress is larger, that means you're closer to your goal, your reward increases from 1 up to 2,981. And the center line, the distance, first you calculate the direction of the center line based on closest waypoint. So the waypoint, you have 2, a previous waypoint and next waypoint. So you're trying to go to the next waypoint. That's your short-term goal. And you calculate track direction and calculate a direction difference. That is your current heading versus the current track direction. And then if direction is greater than direction threshold, then you decrease the reward by half. So don't deviate too much from the track direction. You should try to aim forward. And then max speed, you have 6, and you have 4 different choices of the speed value. So you can also make the speed a continuous value. Then the training is more perhaps more difficult. But by discretizing the steering angle, the heading, and the speed, you're simplifying the problem a lot. If steering less than 7, if speed is 1 equal to speed, reward is 1. If speed 2 equal to speed, reward is 0.8. So you're rewarding faster speed. So that's the speed. And then that's the center line. you have here you have more markers, 9 markers, and the closer you are to the center, the higher your reward. If you fall within the first marker, you have 3.0, and then finally, if you fall within the 9th marker, you have 0.01. So that's distance from center, and then finally you have a total reward as a combination of all the factors. So you're trying to stay close to the center line, and you are trying to steer forward, trying to get close to the goal. So you can see it's a very complex, long reward function, and all these settings seem pretty arbitrary. I mean, why do you set progress at 20, 30, 40% instead of 45%? Why do you set the reward at 20, not 21? So, and 2,981, I don't know where that came from. So it's a magic to set these parameters, to set the reward function. And your IR's algorithm's performance is fundamentally determined by your reward function. If your reward function is not right, then no matter how good your algorithm is, you're not going to work well. So imitation learning is useful when it's easier for an expert to demonstrate the desired behavior rather than to specify a reward function for IL to learn the policy. So for AD in a realistic environment, the reward function would be a huge, complex function involving everything in the environment. So that was just a toy example of a simple track, a single vehicle with no other vehicles, no other obstacles, no pedestrians. So for realistic driving, it's a nightmare to write the reward function. So then many people turn to IR instead. So it requires access to an expert either offline with driving data logs or online with query on demand. So it's also called learning from demonstration. So there are 2 variants. One is learn to mimic the expert's policy, behavior cloning, and direct policy learning. One is to learn the expert's value function. It's called inverse reinforcement learning. Behavior cloning is a form of supervised learning, where an agent is trained to perform a task from demonstrations by learning a mapping, for example, a CNN between states, input data, and actions, the labels. So just like you map from image to a CalDoc label in supervised classification, in a behavior cloning setting, you map from input image to a set of possible actions, run or jump for Super Mario. So you collect demonstrations, talk star trajectories from expert, maybe an expert game player, and you treat the demonstrations as IID state action pairs. State 0, you take action 0. Star means that it's the expert action, so it must be optimal. State 1, you take action 1. And then you feed these state action pairs as data into this convolutional neural network to learn a policy, which policy is a classifier that maps from S to A. And loss function is defined as to minimize the loss between the expert's action and the neural network's policy action, pi theta. Theta is the neural network parameters. So the main difference between SLR, supervised learning, and behavior cloning is that for SLR, the input X for computing the label Y equals Fx is IID, independent and identically distributed. So it's a term in statistics indicating that all the samples in the input are independent. For example, there's no correlation between one input image and next one for a classification task. But for imitation learning, behavior cloning, and Markov decision processes in general, the input, which is the state st for computing action at from a policy function pi theta, is not IID, but highly correlated, since action taken in a given state induces the next state. For example, a vehicle does not randomly jump around, but follows a smooth path. If state st is defined as the current front camera video frame at time t, then there's strong correlation between frames across time, st, st+1, and so on. So the problem is, with BC is mainly caused by the non-IID input data, which means that errors made in different states add up. Therefore, a mistake made by the agent can easily put it into a state that the expert has never visited before, and the agent has never trained on. In such states, the action is undefined, and this can lead to catastrophic failures. So the expert driver always keeps in the center of the lane. That's why he's an expert, right? He drives correctly. So the front camera images, the input data in the training set does not contain views where the vehicle is heading to go off side of the road. So once the vehicle heading deviates a little bit towards the side, you go into a vicious cycle. So the input data is not in the training set. The camera is seeing a view that it has never seen before during training. So the action is undefined. And this causes a random action, which causes the vehicle to deviate even more. And then you keep on going, and eventually this leads to a crash. So we'll talk about how they address this issue. So one, direct policy learning is an improved version of behavior cloning. This assumes that we have access to an interactive expert at training time. So we don't just have a driving log. We have an expert that's available on demand. So we start with the initial predictor policy based on the initial expert demonstrations, the log, and then we execute a loop until we converge. In each iteration, we collect trajectories by rolling out the current policy, which we obtained in the previous iteration, and using these, we estimate the state distribution. Then for each state, we collect feedback from the expert. What would he have done in the same state? And we train this new policy using this feedback. So the key is that now the expert is in the training loop. So previously, we don't have this link. We have access only to a huge pile of expert driving logs, and that's it. But with DPR, we have this feedback loop so that whenever the agent doesn't know what to do, he hasn't seen a training sample before, then he'll go and ask the expert, say, hey expert, what do I do now? I have never seen this before. So expert goes in and tells it what to do, and then it learns. There are two variants of DPR. One is data aggregation, which trains the actual policy on all the previous training data. So Dagger is a well-known algorithm where the expert remains in the loop during the training of the controller. Controller is iteratively tested, and samples from the obtained trajectories are relabeled by the expert. Policy aggregation trains the policy on the training data received on the last iteration and then combines this policy with all the previous policies using geometric blending, which means weighted blending. In the next iteration, we use this newly obtained blended policy during the rollout. So,
Sorry, you have waiting for each state value, right?
No, we're not working on value here. We're working on policy directly.
So you weight different policy as functions of states.
Yes. So suppose this policy says turn left by 5 degrees. This policy says turn right by 50 degrees. And then you may have a combined policy of 5 times beta plus 1 minus beta times 50 divided by and is divided by 1. Yeah. So you have a action from the previous policy, and you combine it, blend it with the current policy. So this is so this policy-based training does not use the value function at all. It's a different approach from Q-learning. So data aggregation Dagger, I don't remember. I think you can do value-based or policy-based. Yeah, I think it's independent of the value or policy-based. But for policy aggregation, I think you can still do value-based, except pi is the argmax of the action of the value. But whatever you do to train the pi in this first line, and then in the next line, you always do this geometric weighted combination. So the other the next approach is inverse reinforcement learning. Start with a set of expert demonstrations. We assume they're optimal because it is the expert. And then we try to estimate the parameterized reward function that would cause the expert's behavior policy. Behavior is pretty much synonymous as policy. So the problem is that the reward function is not unique. Multiple reward functions may lead to the same behavior. So for example, an outside observer sees that you work very hard, that's your behavior. He may infer your reward function to be that you really enjoy your job, but your actual reward function is to earn more money, but you really hate your job. So the outside observer does not he has no way to know that. You may ask, does it matter? As long as it predicts the correct behavior of working hard. It does matter because an agent with incorrect value function won't generalize well in a different environment. So suppose someone trains an agent to imitate you, the expert. The agent has the same behavior as you in the current environment, but faced with a job offer with higher salary, the agent may take a different action from you with the wrong value function. So the general solution is to try to learn the correct value function by observing the expert in the diverse environments. So in this case, you try to offer the expert higher salary and see how he responds, and then you learn from this behavior. So the IIR, the detail is to repeat until we find a good enough policy. So collect expert demonstrations, learn a reward function, and given the reward function, learn a policy using reinforcement learning, and then compare the learned policy pi with pi star, the expert policy, and stop if pi is satisfactory, that is close enough to pi star. Otherwise, you go back and relearn a new reward function. So your eventual goal is to try to approach pi star uh, with pi. So with a function approximation such as a deep neural network, you can do a neural network is a universal function approximator. So you can approximate any function. So IRL, there are two variants. One is model-based. So one is model-free. So model-based, you have a linear reward function, and in each iteration, you solve the full IR problem, which is only feasible for small MDPs. We know the model, which is the state transition dynamics of the environment, so we can easily compare our learned policy with the experts one. And for model free, we assume the reward function is more complex, could be a DNN. We also suppose that the state space of the MDP is large or continuous. So in each iteration, we can only solve a single step of the IR problem. So we don't know the model, but we have a simulator of the environment. So comparing our policy to the experts one is trickier. So perhaps it's not very helpful just reading the description. Maybe I'll come up with some examples next time. So in terms of autonomous driving, here's the classic pipeline. From sensor data, you have a perception module to detect objects, traffic lights, and so on. And then you do behavior prediction of surrounding vehicles, pedestrian, and then you obtain a set of object future trajectories. And then you, based on that, you do planning, which outputs a trajectory, and then the controller has to follow the trajectory by controlling the throttle and steering. So every box here is a separate module. As I discussed before, I mainly discussed a planner and controller. I did not discuss a little bit here, but did not discuss perception at all. So in a end-to-end driving, such as NVIDIA's PilotNet, you have a deep neural network replacing the entire end-to-end pipeline. So takes it takes as input the sensor data and maps it to throttle and steering commands. So the mid-to-mid model, the Waymo's ChauffeurNet, is to have a separate perception module, but replace the behavior prediction and planner with a deep neural network. And then the controller is still a separate module. So the benefit of mid-to-mid is that end-to-end approach, the raw sensor data is the input, the pixels. So they contain extremely high dimensional information with the high definition cameras and the multiple cameras on board. So which can be influenced by different textures and appearances of roads and objects, different weather conditions, and different daytime. So mid-to-mid approach by a separate perception module, they use a bird view representation, which is a concise description of only the useful information for decision making and planning, disregarding the irrelevant information such as texture, light conditions, and object appearances. So that's on the perception side. On the right-hand side, remember, IR needs labeled data in the form of expert driver's action at each time step to obtain a trace of state action pairs as training input. It's a supervised learning approach, so it needs labels. So for the end-to-end approach, you must record expert drivers' low-level actions, steering, brake, acceleration, by tapping into and capturing signals from the vehicle's internal bus. Whereas in mid-to-mid approach, you only need to record expert drivers' vehicle trajectory logs. So if you have end-to-end, then your expert action is these actions: throttling, steering, low-level actions. But if you have a mid-to-mid, then your expert's action is the trajectory, which is much easier to capture. So that's why end-to-end is not very practical, and people generally think mid-to-mid is more more likely, more feasible. So I'll first discuss this paper, PilotNet from NVIDIA in 2016. Is the first industrial strength end-to-end driving research that's more or less successful. All the previous cases were toy, small vehicles. So these are the early projects of IR applied to AD. So Alvin is a vehicle from CMU in 1990. Input is low resolution image. It's a fully connected NN, which is pretty small. Dave is by Yang LeCun in 2003, low resolution image as input. Now the network is convolutional neural network, which is much better at perception. The training method is imitation learning, behavior cloning. Human drives vehicle, records sensor data and human actuator commands as training pairs, and train a DNN to map sensor data to actuator commands, mimicking a human. So here's the right-hand side. This is the input, the image. This is the output, the steering wheel angle. So I do find it strange because PilotNet controls steering only. So I think acceleration, braking are controlled separately, but the paper did not mention it. So here's a YouTube video of PilotNet.
Do you observe that velocity is changing or it's not clear?
It's not clear how they do the velocity change. Obviously, they must do it because they have the vehicle driving in a realistic environment for many miles.
Mm-hmm.
So yeah, this video is not very fun, just to let you see how this thing works, mapping from the image to the steering angle. So yeah, if you notice, it's driving pretty much on a kind of a highway, a pretty wide road. There's a red light. So I don't know what controls the braking. So it doesn't say in the paper. The data collection system. So they have 3 cameras during training behind the windshield of the data acquisition car, and a time-stamped video from cameras is captured simultaneously with the steering angle applied by the human driver. So the steering command is obtained by tapping into the vehicle's controller area network bus. In order to make our system independent of the car geometry, we represent the steering command as 1 over r, where r is the turning radius in meters. So if you remember our bicycle model, there's a formula to convert from the steering angle to the turning radius, right? You have the bicycle here, you have a steering angle, delta, and then you can draw parallel perpendicular lines, and the intersection here is your instantaneous center of rotation, and this is your r. And they're taking 1 over r as representation of the steering command, so that it's independent of the car geometry. So 1 over r, which is the curvature, smoothly transitions through 0 to left, from left turns to right turns. Left turn is negative, right turn is positive. So the training data contains single images sampled from the video paired with the corresponding steering command. So your training, and the steering command is continuous, not discretized. So it's not a classification problem, it's a regression problem. Mapping from images to a floating point number, 1 over r. And then at execution time, you can convert it back into delta, the steering angle. So the problem, as I mentioned before, is that the training data from human driver pretty much always stays in the center of lane. So if the car deviates from the center, the image it sees is not in the training set, so it does not know the correct action. So the solution is to augment the training data with additional images that show the car in different shifts from the center of the lane and rotations from the direction of the road. So the images for the two specific off-center shifts can be obtained from the left and right cameras. Oh, what did I do? Somehow YouTube video is playing. Oh, sorry. So, during data collection time, you have 3 cameras, one facing forward, one facing a little bit to the left, one facing a little bit to the right, with an angle. So, but at operation time, you only keep the center camera. So the left camera and right camera, they capture the images that looks like the car is leaning to the left or leaning to the right. So, and then you can use these images to do data augmentation. You augment the data by adding artificial shifts and rotations to teach the network how to recover from a poor position or orientation. So for the left-right camera image, you have 2 specific off-center shifts to a fixed angle from the center, and then you can do a regression and perform additional shifts between the cameras, and all rotations are simulated by viewpoint transformation of the image from the nearest camera. So it's kind of a computer graphics transformation. The steering label for transformed images is adjusted to one that would steer the vehicle back to the desired location and orientation in 2 seconds. So for example, the image from center camera shows that the car is driving straight. So that's the action of the expert. But the shifted image from left camera shows car is leaning left. And then you associate this left camera image with a synthetic turn right command, even though human driver never issued it. And during operation, if the center camera, remember during operation, you only have a single camera. If the center camera sees this image, the car will turn right. So by doing this shifts, additional shifts between the cameras and all rotations, by viewpoint transformation, you obtain a lot more than 3 images. You obtain the continuous range of different images, and then you can associate artificial steering commands for each such image. So you have a rich set of training data, so that when the car deviates from the center, even though the expert never drove the car this way, you have training data to tell the car that it should shift back into the center. So data augmentation is the common trick used by all the work I discussed today to remedy the shortcoming of imitation learning, to augment the real data with synthetic data to cover the cases that the expert did not cover. So here's the driving simulator. You have a library of recorded test routes and videos and time synchronized steering commands, and then you perform a shift and rotate transformation so this is perhaps going straight, and then you shift it so it looks like the car is leaning left, and then you use this as input to train the CNN, and using a network computed steering, and then the network computed output, the steering command is put into the simulator to update the car position and orientation. So the amount of perturbation, that is how much you shift the image, uh, uh, is a random variable chosen from a normal distribution. So most of the time, you keep the original image and keep the original expert action, but with a normal distribution, sometimes you try to artificially let the car deviate from the center and train the CNN to correct it. So this is PilotNet. It has input plane of 66 times 200 pixel image. It's a color image, so you have RGB value, so times 3, and then you have a bunch of convolutional layers. You have finally 4 fully connected layer, and finally 1 output, the steering angle.
And all these choices are just trial and error, right? I mean, there are no theory how to make these choices of number of layers, number of kernels, everything.
Well, in the computer vision community, there are a few well-known CNN architectures. The earliest one is AlexNet, and then you have ResNet. You have about a dozen well-known CNN architectures that have been shown to work well. So typically, you take one of those and do some tweaking on top of that. So you don't build it from scratch.
Okay.
So this shows the visualization of a salient object. Salient object is which regions of the input image contribute most to the output of the network. So the green part. So you can see that the PilotNet focuses on the same things a human driver would, including lane markers, road edges, and other cars. So you obtain these salient objects by taking out the intermediate values from the CNN and performing some transformations based on the intermediate features to identify the salient objects. So, and then they did on-road testing. So the loaded on the DrivePX platform. DrivePX is their, I talked about in the introduction class, is NVIDIA's platform for autonomous driving. So they achieved a 98% autonomous time and drove 10 miles on the Garden State Parkway with 0 intercepts. Intercept is when the human safety driver takes over control. So let's take a break for 5 minutes before I discuss the next paper. So any questions for PilotNet? Okay. Okay, is everybody back? So let's discuss ChauffeurNet from 2018. This is a mid-to-mid approach. So the abstract, our goal is to train a policy for autonomous driving via imitation learning that's robust enough to drive a real vehicle. We find standard behavior cloning is insufficient for handling complex driving scenarios. Even when we leverage a perception system for pre-processing the input and a controller for executing the output on the car, 30 million examples are still not enough. So that corresponds to 60 days of continual driving. So we propose exposing the learner to synthesized data in the form of perturbations to the experts driving. So again, you see synthesized data, which creates interesting situations such as collisions and or going off the road. So rather than purely imitating all data, we augment the imitation loss with additional losses that penalize undesirable events and encourage progress. The perturbations then provide an important signal for those losses and lead to robustness of the learned model. So the architecture is the neural net sits in here, and then the input is from data renderer, which gives it a bird eye view, a top-down view. And then the output is the predicted waypoints, not the steering and a steering angle we saw before. And then the controller tracks the waypoints and feeds it into the vehicle simulator and updates the environment by moving. So the neural net is sitting in the middle. So here's the experiment with pure behavior cloning. So the vehicle, ego vehicle is here. It's driving, it encounters a yellow obstacle vehicle. It gets stuck, doesn't know what to do. Here you have a curved road, and the vehicle it goes a little bit off road, and then it gets stuck. It has never seen this image before, so it doesn't know what to do. So the blue dots are the past positions, and green dots are predicted future positions. But with the ChauffeurNet, the car is able to navigate around the obstacle car and around the curved road. So the ChauffeurNet input is a mid-level input representation. So you have a separate perception system that processes raw sensor data, sensor information, and produces the output, a top-down representation of the environment and the intended route, where objects such as vehicles are drawn as oriented 2D boxes, along with a rendering of the road information and traffic light states. Uh, so we present this mid-level input to a recurrent neural network named ChauffeurNet, which then outputs a driving trajectory that's consumed by a controller, which translates it into steering and acceleration. So here's the ChauffeurNet input, output in detail. So input is the road map, traffic lights, speed limits. So this is the information from high definition map. And then perception objects, current agent box, an agent pose history, its recent past trajectory. So these are obtained from a separate perception module. With LiDAR, you have iterative close point algorithm. With cameras, you have perception CNN algorithm. So you do sensor fusion and then extract this top-down view. So this plus the planned route, the intent is combined as is input to the RNN instead of the raw camera images like in PilotNet. And then the output is predicted waypoints, predicted future poses. And then this is fed into the controller to track the waypoints. So it's a mid-to-mid approach because you need a separate perception module on the left to produce these abstract top-down views. These may be obtained from a high-definition map. You need a separate controller module on the right because you're only outputting the waypoints, not the actual steering and braking commands. So this view is obviously much cleaner, much more informative for autonomous driving than the camera view, which can be very noisy. So this is the animated input and outputs. So top row are these things I discussed before. The intent is the ego car should turn right. The bottom row is the current agent and dynamic boxes of nearby cars, which is a history of past 1 to 2 seconds, past agent poses. So before this agent was in this position, it's a recent past pose for a few seconds, and output future agent poses, the desired reference trajectory. So all these are inputs, and the last box is the output. ChauffeurNet is a convolutional recurrent neural network consisting of the CNN-based feature net for extracting features from the bird-eye view and agent RNN. It's trained with behavior cloning. Yeah, it's an enhanced version, so I would say it's IL, imitation learning sounds better. Guided by ground truth data, which is the expert driving logs and loss functions. So yeah, this is describing this figure. So the ChauffeurNet has a feature net, which is CNN and RNN, agent RNN on the left. So the training loss function, you have heading loss, which is the target agent heading from the expert driving log, and the actual heading. The difference between the actual and expert heading, and difference between a speed and the target speed, waypoint and target waypoints, agent box, heat map, and target agent box, and so on. So it's supervised learning. So all these green parts are known from the expert driving log. So you're trying to mimic the expert. So here's the ChauffeurNet model. You have FeatureNet, the CNN, and then you have the RNN. It takes as input the features from the CNN. Could be cars, pedestrians, high-level features, and then the past agent locations, the recent past trajectory, and the memory module. So yeah, so you have feature F, and K is the iteration number. And the last agent box in the bird eye view, and output the predicted location and predicted agent box with the heading information. And the memory module, if you are familiar with RNNs, RNN can have a separate memory module to keep track of history. So the memory module here is to keep track of the recent, I'm not sure, let me see. Recent past, no, this is the past agent location. The memory module is recent predictions. Yeah, the memory of past predictions from the agent RNN. So if you're not familiar with RNNs, the details are not important. So the important thing is that compared to PilotNet, which is a CNN, I think here I should write something. So so it takes a current camera image and maps it to a steering angle. No history. Information is used. So the camera, it captures the video, right? But it's just taking the current static image, ignoring the video part. And ChauffeurNet uses RNN and exploits the history, maybe past a few seconds, to make better predictions and decisions.
But past, not past images, past prediction, right?
The RNN takes into account the history of past predictions and also the past agent locations. Yeah, so here's the past location, the position, the past trajectory. Here's the past predictions. Both are input into the RNN.
Uh-huh.
So, and then we come back to the old problem that we need to synthesize synthetic data to handle the problem of the agent seeing something unfamiliar. So you try to synthesize some weird situations to train the agent. Uh, and then they added another a bunch of loss functions, imitation dropout. So trajectory perturbation is to run the model as part of a closed loop system over time. Uh, so can cause the input data to deviate from the training distribution. So that's the old problem we saw before. So now they add realistic perturbations to the agent trajectories. So here's the original logged training example where the agent is driving along the center of the lane. The perturbed example, so this is the agent going this way. The green is the planned trajectory. I think the white is the past trajectory. Uh, and in this case, the perturb the agent location, the red point, uh, in the original example away from the lane center and fitting a new smooth trajectory that brings the agent back into the original target location along the lane center. So if you look at it closely, this trajectory has a little bit of a shape here. Well, this one is straight. So the Hill expert driver is driving straight. But you need to make the learning trained agent more robust. So you add artificial perturbation to move it away from the center of the lane. But then the expert has never done it. It's not in the driving log. What do you do? So you fit a trajectory like a spline or some other trajectory planning method we discussed before uh, to pretend that's the expert trajectory, and then use that as part of your training data. And then they added a whole bunch of different loss functions. So for example, I just discussed this collision loss. Since our training data does not contain any real collisions, the idea of avoiding collisions is implicit and will not generalize well. To alleviate this issue, we added a specialized loss function that directly measures the overlap of the current predicted agent box BK with the ground truth boxes of all these seen objects at each time step. So this is a intersection operator. So if there's a non-zero intersection, then it means there's a collision. You penalize that. And then you have loss functions for trying to penalize when you go off-road, or a bunch of other loss functions that you wouldn't have for a expert driver. So the imitation dropout. So So the losses are now separated into two groups. One is the imitation loss we saw before. The one is these losses. Yeah, on the left are the imitation losses. So you're trying to imitate the expert, and the larger your deviation from the expert, the higher the loss. On the right are the environmental losses. So here these are the loss functions you added yourself to to discourage undesirable behavior such as collisions. Imitation losses cause the model to imitate the expert's demonstrations. To further increase the effectiveness of the environmental loss, we experiment with randomly dropping out the imitation losses for a random subset of training examples. So during imitation dropout, the weight on the imitation loss is randomly chosen to be either 0 or 1 with a certain probability for each training example. So the overall weight loss, here they use loss function. As I said, it's just a minus the reward function. So the overall loss is weighted sum of the imitation loss and the environmental loss. So sometimes you set the W imitation as 0, so you only care about the environmental loss. So here's the experimental result. M0 is the imitation with past dropout M1, and yeah, M4 is the with dropout probability of 0.5. 0.5% of the 50% of the time you set the weight of imitation loss to 0. And trajectory perturbation, environmental losses. So different models, they call is pretty typical in machine learning to have the ablation studies, where you cut off some factors and add on one element at a time to see which element is contributing to your performance improvement. So you have a bag of 10 tricks. You apply one trick at a time and measure each case to identify exactly which trick is working. So yeah, as you add more and more tricks, then the for different scenarios, nudging for a parked car, and so on. And the more tricks you have, the better the performance. Pass is green, and blue is stuck. Yeah, it's not monotonic. There are some. Yeah, one is M2 with less imitation, one is with imitation dropout. So they're different. Okay, so that's ChauffeurNet. Any questions? Okay, so let's move on to this paper. This is from UC Berkeley, also a mid-to-mid approach. So manual policy may be suboptimal and expensive to develop and maintain at scale. So with imitation learning, we only need to collect data, and then the computer will learn and improve the driving policy automatically. However, current imitation learning methods are not performing well. Moreover, the safety is not guaranteed when we use a DNN policy. So we propose a framework to learn the driving policy in urban scenarios effectively given offline collected driving data with a safety controller incorporated to guarantee safety at test time. So here's the framework. So you have a separate perception module and routing module to plan the route and generate a bird eye view. Actually, this is exactly the same as a chauffeur net, at least this part. And outputs a planned trajectory using DNN policy network. And then you have a safety and tracking controller to calculate the safe control command to be applied to the vehicle. So the planned trajectory is output from the imitation learning module, and just like before, but instead of a simple tracking controller, as in a chauffeur net, you add additional safety controller to keep this control command within the safety region to avoid collisions as a last check. So let's first talk about the deep imitation learning. So actually, I don't know what's the difference between ChauffeurNet and this one. They look the same to me. And they this one came out in 2019. So it did cite ChauffeurNet, but didn't say exactly what's the difference. So the bird's eye view observation combines information of HD map, routing, traffic light, historical detected objects, historical ego states. And then you go through a deep neural policy to get a planned trajectory, which can be tracked by a low-level controller, such as the PID or MPC. Oh, okay. Yeah. So the architecture is different. So VGGNet is a well-known CNN architecture. So you can versus the RNN, convolutional RNN. In ChauffeurNet. So that part is different. So the output has each hidden units corresponding to each predicted trajectory points. And loss function is to minimize the displacement error between the expert's motion trajectory point position and predicted point position. So that's the same as before. So you're minimizing the deviation from the human expert. Here's the expert is not a human, but it's an expert. You're trying to track, to mimic the expert.
It's the same as waypoint that you called before, right, or not?
Yes, it is the waypoint. So they are a university group. They're not Google, Waymo. So they don't have expert driver to work for them. So what they did is to use a model-based controller to act as the expert in the Carla simulator. Carla is a well-known driving simulator. So the controller performs normal urban driving behaviors and make random turns at intersections. So the Eagle vehicle is running. We record the rendered bird eye view images and the corresponding Eagle vehicle states. That's global positions and yaw angle, which is the heading, every 0.1 second. So the model-based controller, they didn't say exactly what that is. I think it's the traditional planner.
Sorry, Carla is the one we studied in RSS, right?
Oh, we saw that.
Yeah.
Yes, we saw a screenshot of Carla before. Yes.
Yeah.
And yeah, again, you see this perturbation trick. You introduce control noise to the expert controller during the data collection phase. You add the noise periodically every 8 seconds and lasts for 1 second to push the vehicle's pose away from the waypoint. And the expert then provides demonstrations of recovering from perturbations. That's the model-based thing, traditional pipeline. And the states during the noise phase are removed in order to not to contaminate the data set. Okay, so that's the perturbation part. And then given the planned future trajectory in the future horizon 1 to h from t+1 to t+h, the tracking controller, this guy, outputs the desired acceleration at and steering angle delta t to drive the vehicle to follow the trajectory. So at any given time, you pick a specific point in the trajectory. They pick m equal 5. So you pick x at t+5, y t+5, and aim for that point in the planned trajectory, and you do it at every time step. So the tracking controller is decomposed into longitudinal and lateral controller. Both are PID, so it's very conventional. Longitudinal controller, so the target speed is the distance, Euclidean distance between the two neighboring waypoints. So this is t+6, this is t+5. And then you divide it by the time dt. So that's your target speed. A desired acceleration is obtained to minimize the difference between the current speed and the target speed from the planning, from the DNN produced reference trajectory. So lateral controller
I'm sorry,
to,
this VD, it's taken also at the particular moment t+6 or t+5, or it's always constant?
yeah, VD is the desired velocity at time t+5.
Okay.
Yeah, actually between time t+5 and t+6. It's a little bit strange because you're trying to make VT equal to VD, which is time t+5. I guess if the dt is very small, yeah, it makes sense. So the lateral controller simply tries to minimize the heading error. So suppose this is your x t plus 5, y t plus 5. That's the waypoint you're aiming for, and that's the current that's the current position. And then your heading is pointing this way. This is your actual heading, and you're trying to penalize this angle here to try to minimize it. So this is done with the heading error is from this formula is arc cosine of x dot y divided by xy magnitude. So they wrote a whole bunch of formulas here just to express this point. So the end target is the unit vector pointing towards the target, and the n eagle is the unit vector pointing towards the current heading, and then you minimize their dot product. So the safety enhancement controller, so the acceleration and steering command from the trajectory tracking controller does not guarantee safety, no collisions to other agents. This could be due to a number of reasons. Could be that the deep learning imitation learning planner did not give you a good trajectory. Perhaps the trajectory has a collision. Perhaps the perception module is not perfect. So yeah, could be the tracking controller itself did not work very well. So in any case, the tracking controller is trying to track the planned trajectory. Uh, uh, so it's not really aware of obstacles and collisions. And then they added the safety controller afterwards and modified the alpha t and delta t to enhance safety if their original values are not safe. So the approach is to calculate a control safe set US if control command UT, the alpha delta, is within a safe set, then it's guaranteed to be safe. So a safety index is computed as the function of vehicle state x, which includes the ego vehicle x0 and surrounding object xj. So the safety index is defined as the small d, the distance between these two vehicles, center points. So P0 is the position of ego vehicle, and Pj is the position of the surrounding object, the neighbor vehicle, and Q is a matrix such that this product is equal to 1. So this particular formula encodes the ellipse around the surrounding vehicle with long axis equal to 1 and short axis equal to 1 over beta. And then you have a weighting parameter alpha, which is a tunable parameter, so that as long as this phi is less than equal to 0 and d greater than equal to 0, it's safe. So if phi is less than equal to 0, it means that these two cars have keep a safe distance. So for visualization, so the safe region based on safety index, that is phi x less than equal to 0, it roughly visualizes like this. Here's the ego vehicle. The safe region is here, assuming that the other vehicle is turning right. So yeah, and if you have a pedestrian, and then you can compute the safe region like this. So the safety index less than equal to 0 means that this value is higher than equal to d. So which means that the larger the distance between the two vehicles and the larger the relative speed d dot, If it's positive, then they're moving away from each other. So the weighted sum of them is higher than the threshold. Then it's safe. Here's one case where it's large enough, so it's less than 0. It's safe. This is unsafe. It's too close. And then with boundary constraint, so you have a wall on the side. You have an additional phi here, and with relative motion, you have the d dot factor to take into account. The motion is towards or going away. So with the same, yeah. So this reminds you of RSS, right? So the responsibility aware safety.
So they need to predict not only its own location and speed and velocity, but also all the obstacles, well, and all other objects.
Yeah. So where do they do that? It doesn't show here. So this in this image, the deep imitation learning planner is just predicting the current vehicle's trajectory. Where does it predict the other vehicles? It doesn't say. Yeah, they should predict it. Otherwise, you can't get the d dot. So the safety state safe set and control safe set. State safe set is a level set that is for all x, phi x is less than or equal to 0, which is same as this. So it injects eclipse constraint as we saw before, and considering the relative speed between the ego and surrounding object. Control safe set is the control inputs such that it keeps the that keeps the state in a safe set. So if phi starts with is it right? I think I perhaps made some typo here, but yeah, but I should keep phi less than or equal to 0. Yeah, so if the if we approximate the ego vehicle dynamics to be a control FM function, and then the control safe set can be written as this, which is a much simpler and enforceable constraint. You just simply take the derivative of phi, and you have two terms, and you plug in x 0 dot, which is the ego vehicle's dynamics, and then rearrange the terms. Less than as phi x phi. Okay. So, and if there are multiple surrounding objects, we can calculate the intersection of the control safe set for each object, which is a convex polytope. So the paper contains some typos. Yeah. And then you have the trajectory tracking controller generated the control command which may be unsafe. The safety controller maps it into the control safe set US by solving a quadratic programming problem to stay in the US, that's the argument, that's the constraint, while minimizing its deviation from the potentially unsafe UT. So that's this term. And W is a weighting matrix. So the U star is guaranteed to be safe because it's within US. At the same time, it tries to stay close to UT as much as possible. Finally, you obtain the safe control command to be finally applied to the actuators. So that's the, if you look back at the figure, so the safety controller takes into alpha t delta t and outputs alpha t star delta t star for collision avoidance. We have one final paper. So this one is relatively simple. So I think we'll just go through it. So this is end-to-end driving with conditional imitation learning. So standard IR is to have training data as a set of observation action pairs generated by expert. Then we train a function to mimic expert actions, mimic the loss between the expert action AI and our function output. So here the paper uses a different notation. Observation is just the state we saw before. For example, the video captured by a front camera. So the implicit assumption of this formulation is that the expert's actions are fully explained by the observations. So there exists a function that maps observations to the expert's actions. So it works well if the assumption holds, for example, for lane following. But for more complex scenarios, the assumption breaks down. Consider a driver approaching an intersection. His subsequent actions are not explained by his observations, the front camera view, but additionally affected by his intention. Do I want to turn left, go straight, or turn right? So the same observations could lead to different actions depending on his intention. So at training time, the command is provided by the expert, left, straight, and right, a few seconds before reaching the next intersection. So for example, human drivers already use turn signals to communicate their intention when approaching intersections. These turn signals can be used as commands. So the training dataset becomes observation, command, and action. And command conditional IR objective is to minimize the difference between the expert action and the function output. So at test time, the commands may come from a human user, a passenger, or a high-level planning module with A star or Dijkstra. So they can affect the behavior of the controller in two possible architectures. So let's look at their video.
End-to-End Driving by Conditional Imitation Learning by Felipe and Antonio from CVC, Matthias from KAUST, and Vladlen and Alexei from Intel Labs. Conditional imitation learning allows an autonomous vehicle trained end-to-end to be directed by high-level commands. We train and evaluate robotic vehicles in the physical world and in simulated urban environments. The vehicles drive based on video from a forward-facing onboard camera and high-level commands such as turn right at the next intersection.
Here, the the command, they consider 3: turn left, turn right, go straight, before each intersection.
The trained controller handles sensory motor coordination, staying on the road, avoiding collisions, and follows the provided commands. We first evaluate our proposed method in a photorealistic simulation environment. A high-level planner provides commands such as turn left at the next intersection. The driving policy predicts vehicle controls while taking these commands into account. Next, we implement our method on a robotic vehicle. The map to the right shows the primary route used for testing the robotic vehicle. Intersections traversed by the vehicle are numbered according to their order along the route. Colors indicate commands provided to the vehicle when it approaches the intersection. Blue is left, green straight, and orange is right. The vehicle is now guided by a human operator who communicates commands through an indicator signal. Like in a real car, these commands are usually given as the robotic vehicle approaches an intersection. A command can be set at any time, and the vehicle will only act on it once it actually reaches an intersection. As long as there is no intersection, the robotic vehicle will follow the lane regardless of the active command. In our experiments, the vehicle was able to complete the course at every attempt. Generalization. We evaluate how our model generalizes to previously unseen environments with very different appearance. The robotic vehicle is able to consistently follow the lane in all tested environments. The vehicle is also able to take various turns in previously unseen environments. Here the robotic vehicle must navigate a much wider road and responds by aligning with the boundary. In addition, the vehicle also has to transition to a differently textured road while traveling. Lastly, we put the vehicle in yet another environment where it has to master 2 quick consecutive turns. Even just following the lane is difficult here since the road is very narrow and slippery due to the gravel. Please come visit our poster.
So yeah, this paper is pretty simple. Yeah, and they have 2 architectures, where first is the command serving as input to a fully connected network, along with the CNN providing features and the measurements. Measurement is a low-dimensional measurement such as car speed. They are all input into the fully connected neural network, and it generates action, which is a tuple of a steering angle and acceleration. A loss function is the difference from the expert demo. And they can also have another architecture where the command is used as a switch to choose from 3 different possible actions, 1 for turning left, 1 for going straight, 1 for turning right. Yeah, but in any case, the command is used as input. So here I wrote, shouldn't the high-level planner always be present in any AD system? So we saw that this driver intent is present in ChauffeurNet. In ChauffeurNet, we had a oh, this is not ChauffeurNet. Yeah, yeah. So yeah, the SureFornet, if you remember, the one of the inputs is the planned route, which is turning right in this case. So this is an input from perhaps a high-level planner. So I think this kind of input should be present in any end-to-end, even end-to-end driving system. Otherwise, suppose you need to traverse 10 intersections from home to your office, then if you don't have the high-level planner to have a route, I mean, how do you choose the route, right? So I do find it a little bit strange that, well, yeah, so I guess it's present, but in this particular paper, the C, the command is used explicitly in either this way or this way to affect the action. In this imitation learning framework, I think perhaps that's a little bit different from the other work. And then we see the data augmentation, the old trick we saw before. So you add noise. So yeah, the red is noise. The green is the driver's steering signal, and then you add them up to get the blue, the actual driver's control and noise, and then the driver's view at 3 different points in time. The noise causes a drift. The blue drifts to the right, yeah, at point time A, and triggers a human reaction to correct it, and car recovers. So yeah, so this kind of trick is used to enhance, augment the data to cover unexpected situations. So here's my comparison among these papers. View representation, PilotNet and Cordivella use the front camera view. The SureFornet and the Berkeley work use a bird eye view, which helps simplify the visual information while maintaining useful information for driving. DNN, PilotNet, and Cordivella, the last one, are end-to-end, while the SureFornet and Chain are mid-to-mid. So DNN used for behavior prediction and planning to generate trajectory. DNN architecture, all three of those use CNN, and SureFornet uses convolutional RNN with explicit memory taking into account recent history. So the CNN uses the current image as input. I find it strange because it's a common trick when you are doing video analytics. You can input the past history of n frames stacked together as the CNN's input to capture recent history. Why don't you do that? It could be better than taking the current snapshot. And additional things are Cordivella uses a conditional variable to help with the decision process at intersections. And Chain's contribution is mainly the safety module that limits the final control command to the safe set. Otherwise, the rest seems pretty standard. Okay, that's it. Any questions?
Just too much information.
Yeah. I think someone complained about it before. Have too many slides.
I mean, Mr. Zongwa, my knowledge about artificial intelligence is merely limited to introductory subject that we took in term 1 that was like 6 months ago. I found some good videos on YouTube, Deep Lizard, that were teaching the concepts Mr. Kale kindly was teaching last time. But it takes a while till you get familiar with all these concepts. Let aside their accumulated amount and diversity.
Yes. So yeah, I mean, I didn't really cover the basics of machine learning, while Kala focused on the reinforcement learning part, but not the more general deep learning part in this in his lectures. So I mean, for autonomous driving, there are many online courses, online materials, textbooks on the classic approach. So we have the three approaches, right? The classic approach, many courses. For the imitation learning or reinforcement learning approaches, they're all only research papers. NVIDIA's work is the first industrial strength end-to-end training of deep neural network for driving. For perception, it's very mature. I mean, you can recognize images, recognize objects, that's fine. But for action, for the planning, it's pretty new. From 2016, pretty much it kicked off by NVIDIA's paper. So I can only discuss research papers on this topic.
Well, I found on Udemy some courses regarding autonomous vehicles. I registered in them, but it will take a time for a mere beginner. I don't know how many people are like me, similar to my condition. Merely, it's introductory artificial intelligence from the first term that makes my background about the whole subject of artificial intelligence. And in the syllabus, they allow us to register this subject based on that background, but I don't know really how competitive for people like me would be in this part of autonomous vehicles, the machine learning stuff.
Actually, you mentioned the Udemy course. Actually, I know that course. I saw the outline. Their approach is the imitation learning, behavior cloning. So they do the most classic, simplest behavior cloning. They capture a trace of human driver, or you can drive the simulator car, and they capture the trace and train a classifier to map from the input image, from camera image to the action. So they don't have any disturbance, augmentation, or any RNN or any other tricks we discussed in this class. So they follow a strictly classic behavior cloning method.
Is it the course called Machine Learning, Data Science, and Deep Learning with Python? Because I think this is the one, or maybe no. Sorry.
I think it's yeah, this one.
Mm-hmm.
Well, okay, not even this one. This one its name is really misleading because it's really talking about perception only.
I see.
Yeah, recognizing traffic signs. And the other one is on behavior cloning.
Yeah, I think, yeah, this one where you have the two persons, Rian Ahmed, I think, and the, yeah.
Yeah, this is also vision only. Yeah, anyway, so yeah, so I understand your point. So I think maybe I stuffed too much content into these lectures. So
I think overall, I'm truly impressed by the content you are giving us. I just pray to God that I will be. I'll find a way to absorb all this and understand the concepts. There is a lot of helpful videos on YouTube regarding basic concepts of machine learning, the Q learning, and the Markov algorithm, and all that stuff. I mean, that might help to reduce the alienation I feel towards all of this machine learning content. It's
yes, yes. So for the lecture content, I'm not expecting students to grasp every detail. So I think as long as you capture the say the salient points, the view representation, a front or bird view, right? Is it end to end or mid to mid? CNN or RNN. So as long as you grasp the high level concepts, you can ignore the details, especially for the safety index computation. Even I am not sure if the formulas are correct. So you just understand the key concept that, okay, you have a safety controller here for collision avoidance. I think that's enough.
I tell you the truth, sir. Even when it comes into the PID controller and some concepts in it, I couldn't understand the equations fully, but I just grasped the general idea. I managed to do some tasks like changing the shape of the track from complete classical racetrack shape into somehow circular shape. I think in lab 2, when you were saying circular, you didn't mean uh, exact circle shape, because the best you could get maybe is something more like an oval shape, between oval and circular shape, right?
No, I meant a exact circle. Why would you say it's not possible?
Because when you were doing your this red shape, I got the exact one like it when I changed the shape of the racetrack to be as circle as I can, and then increased the speed to 10. I got the very exact shape as this one.
Yeah, but did you tune the PID controller with Twiddle?
Yes, it is with Twiddle. This was the shape I got from the PID when I increased the speed to 10, and this was a PID with Twiddle.
So you also did the DT update I showed in the slides.
But the DT.
Yeah.
In the slides, you were sorry, in this lecture note, you were saying that we increased the number of n
Yes.
To get the shape away from this red one. I increased it to a certain number, and I got it for general DT.
Did you do these updates?
No, I thought that I got the most updated lecture note, control lecture note, but I don't have this.
But did you get all my announcements?
Yes, yes, I know. I went into the L3 lecture note, and I downloaded it, but it seems that what I downloaded wasn't the most recent one.
But after my my announcement from lab updated, this particular announcement was sent on April 24th. So that's when I updated that page.
I think you updated it maybe 3 times, right? The same. This lecture note L3, you updated 3 times.
I may have updated it after April 24th, but that's just a very minor corrections of typos. But for the major, this particular page 34, 35 is on there on April 24th.
Yes, I remember I saw this one, and I looked at page 34 and 35. As I could remember, they were about twiddle and run. Yeah. No, sorry. What I have 35 is different, but twiddle, yes. So.
Okay.
Okay, it's my bad. I will have to fix it somehow. But when I tried to do it as circle as possible, I didn't get a shape that is very circular. I got the shape that is somehow a little bit oval.
Yeah, I think it's because maybe you should add these into your code.
Okay. Okay, I will try to fix it today before I handle it to you.
Yeah, given your situation, a few days late should be okay.
I will do everything in my capacity to sir. Sorry for that.
Sure. You know what? For the lecture slides, I think I should put up a some kind of
version
that can ignore.
Okay. Maybe also if they are updated, if you can kindly put the version that lecture 3, version 3, version 2. So maybe this would reduce such a mistake like that one which happened, sir.
Oh, okay. That's a good idea. So
Yeah.
if I make any large updates, I'll send out announcement. But for minor grammar fixes, I often just fix it.
Yeah.
Yeah.
Yeah. No worries. Thank you very
Yeah.
much for understanding.
Yeah. So I'll put up this kind of thing for unnecessary details on certain slides. Yeah.
Thank you.
Sure. Okay, any more discussions? I think we lost quite a few people. Many people are still here. Okay.
Can you just say basically, so the current state of the art is more or less illustrated by this paper? Is that what everyone do in autonomous driving right now? I mean, everyone
well,
uses machine learning, or it's not, or there are some some teams that use conventional approach.
conventional approach.
The first one that you have, the traditional one that you're saying.
Oh yeah, sure. So I think the state of the art perception, pretty much everyone uses deep learning for the perception box. For the rest, planning and control, it's not really adopted in industry besides a few startup companies. So the paper by NVIDIA and Waymo, I think this end-to-end or mid-to-mid approaches are not in their production vehicles. Their production vehicles are relying on traditional pipeline. Classic.
Okay. Okay, thank you.
So,
but you believe it's the future, do you?
Many companies believe it's the future. A few, yeah, I forgot which one. So they focus on reinforcement learning or imitation learning. These two are closely related. So, but they are the minority. So I don't know.
Okay, thank you.
Okay, so let's call it a day and happy. What's the holiday for tomorrow?
It's already starting, I guess. But yeah.
I mean, what's the name of the holiday?
It's Valborg in Swedish, but I don't know the English
Okay.
name.
Sure. Okay. Happy holidays.
Yeah. Happy holidays.
Goodbye.
Bye-bye.
Bye.
Happy holiday. Thank you.
Thank you.